topic, a lot of different stuff from what you've seen before. So, guide to these notes. Remember, this is a notes guide. You have to write your own notes. So, first thing here, weight. Okay, so weight is a force from an object. So you imagine, you look at this guy here. He's got a weight going down. Okay, W. These masses on each end, they've got weights, and the bar itself has a weight. Okay, so it's actually a force. If there was no ground, then he would actually accelerate downwards. Okay, but because there's a ground, there's an upwards force that's going to balance with that weight force. What's the definition of weight? Okay, essentially you just have to look at the dictionary for that, but it's related to how much force someone provides depending on their mass. Now, where do they actually get this force from? Well, the force only happens when you're in a gravitational field. So if you weren't in a gravitational field, then you wouldn't get any weight. So that means the definition must also then have something to do with a gravitational field. So the actual weight definition is the force acting on a mass due to its due to a gravitational field. A good question here would be, do satellites going around the Earth, do they have weight? And in fact, they do. You've got to remember that even though there's the Earth here and you've got a satellite here, there's still a weight force. The only reason they feel weightless, the people that might be in the satellite, so like in the International Space Station, they might feel weightless because they're in constant free fall. Okay? But if you stop the satellite, it will still fall straight back to Earth. Okay, what's the formula for weight? Okay, so we can just say W equals mg. Where does that come from? Well, if we relate weight as a force, that's equal to a mass times some sort of acceleration. So gravity is an acceleration. Okay, sorry, it should be an A. So this is the one you're looking at there. W equals mg. Unit. Well, if you look at it, it's you can have kg ms to negative 2 if you work it out from the formula. Okay, mass times an acceleration, so it's kg's multiplied by ms to negative 2. But we know it's a force, so it's just newtons. Okay, is a vector a scalar? Because it's a force, it must be a vector. Because our mass is placed in a gravitational field, it will be attracted to the Earth. Okay, so we are put inside a gravitational field of the Earth, and because of that, we've got something called weight. Okay, gravity is essentially the value or the size of the gravitational field at the point we're at. So if you're on the surface of the Earth, the size of the gravity is 9.81, but it's your weight that is actually the force going downwards. Okay. For example, calculate your weight on the Earth and the Moon. Okay, so gravity on Earth is equal to 9.81 ms to negative 2, or you could say 9.81 newtons for every kg. So weight equals mass times gravity. So let's say I'm an 80 kg person, you multiply that by 9.81. Okay, on the Moon, okay, we're saying that G is 1/6 that of Earth. Then it'll be mass times G, which is, well, let's say Earth's G. Let's do an E there. Okay, divided by 6. So it'll be 80 multiplied by 9.81 divided by 6. Okay. And in this case, remember this here, please don't forget that 1. Okay, it's 9.81. Center of gravity, what does it mean? Okay, if you look at some pictures here, there's some good objects that have that are balancing, and the center of gravity is directly above their pivot point. Okay, is based around the pivot point, and so it's actually going to be balanced So what's the actual definition? Well, it's the point at which the whole weight of the body may be thought to act. Okay, so the point at which the whole weight of a body is thought to act. Okay, so if you imagine these objects here, in this pair case, okay, the weight's going down there, the weight's going down there, the weight's going down there. So in all three of these cases, as you rotated the pair, okay, so the pair's been rotated around, the weight is always going through that X, okay? It's always going through that central position. So things like this bird here is balanced on every side of that finger, okay? So it is, so the mass distribution essentially is equal in all directions from that finger, okay? So the weight is considered to act down that point. Here's some other objects, okay? If you look at this one here with the bar, it's quite good. Okay, usually if it's a uniform bar, then the weight will be directly in the middle, but because of this one here, all the weight will be considered to act there. If you rotate the bar around, okay, it's still going to be considered to act through the same spot. Even here, when you've got a flying hammer, okay, it's actually the projectile motion of the center of mass or gravity will be the thing that you're looking at. Okay, momentum, okay. Essentially it's how hard it is to stop something, okay. When you say an object has a greater momentum, is usually when you're trying to decelerate it or apply a force to slow it down, you must apply a larger force to slow it down at the same time as another object if it's much larger momentum. So let's look at this bus here. If they're both going at the same speed, let's say 1 meter per second, then which one is the hardest one to slow down? Well, it will be the bus, okay, because it's got a larger mass. But it also can work the other way. If this car, let's say, had a 201 meter per second speed, then it would be much harder to slow down the car because of that speed it's going at. So what's the formula for momentum? Okay, it's P equals mv. Okay, it's straightforward. So that's that one is momentum. Okay, what's the unit? The unit is, looking at the formula there, is just going to be kg, okay, multiplied by velocity, okay, so kg ms to the -1. That's your unit. What we're looking at now, vector or scalar, okay, is it a vector? Yes, it is. Okay, because if you imagine you're trying to stop something, if the object wasn't coming directly at you, if it was coming at a bit of an angle, the force you have to apply may be in a larger, okay, and the direction of that force is also important. So that means momentum does have a direction, because the direction it's going will change the requirements to slow it down. So let's have a look at these two things. Calculate the momentum of the following things. Which one is the hardest to stop? So it's just using the formula, P equals mv. So this will be 10 times 10, 1, 2, 3, 10,000. Okay, so we're just adding another 0 on there. So, okay, and kg ms to -1. Here we go, you've got a cheetah, looks like. So, P equals mv. So this is 23 times 100, so 2300 kg is the -1. So far the train is much harder to stop, even though that cheetah is moving pretty quick. It is still able to stop it. Actually, I suppose it's a leopard, is it? Anyway, doesn't matter. We'll leave that to biology. So P equals mv. So what's the mass in this one? Very large mass. let's just extend that page. Multiply that by 1, you're left with this as your momentum. Oh, 1 more 0 there, probably. kg ms to -1. So which one is the hardest to stop? Well, it's going to be the tanker. It's going pretty slow, 1 meter per second, but it is many more times harder to stop than a Leopard or a train. Okay, mass. What is it? Well, we'll talk about this in class, but we don't actually really know where mass comes from, but we can know what mass does. Okay, so effectively it's the value for how hard it is to change the motion of something. Okay, so let's say we look at an object that's very heavy. So here's a very heavy object, heavy, versus something that's very light. Okay, and they're both stopped. Which one on a frictionless surface will be the hardest one to get started? Okay, it would be obviously the heavy one. Okay, so changing motion from 0 at rest to another motion is much harder for a heavy object as opposed to a light object. So it's a value for the resistance. It could be any sort of word here. The resistance to the change of motion for an object. What is inertia? Well, inertia is essentially the same thing, okay, except let's say mass is the value and inertia is the concept itself. Okay, one important thing here, mass is not the amount of a substance. Okay, very important that. What is the amount of the substance? It is the mole. Okay, chemistry. Newton's first law is a goodie. Okay, essentially because of inertia or mass, things don't want to do anything. Okay, they actually generally want to stay where they are. They don't want to change their position. And once they're actually moving, they actually want to keep going forever. Now that's the hardest one to understand. The only place you can really see that is in space. If you get an object moving in space, then it'll keep going forever. But looking at it here, we've got some examples of Newton's first law. I'll get you to write it down, but essentially it says a body at rest or in constant motion will continue in that motion unless there's a resultant force acting on it. So this experiment here, with the guy with, he has a object that sort of has two heavy masses connected to a wire that bounces off his head. So there's like a little pivot point in the middle of his head. Okay, so let's just change color. So in the middle of his head there, where that thing's just come up, which is really annoying. Let's go, okay, put that away. So in the middle of his head there, it's actually like a pivot and it's free to rotate. So with this object, it's quite a good little experiment. You can actually just turn your head around and the masses will stay where they are. So this guy could start looking out this way, okay, or he could be looking backwards. This is a little experiment here. It's sort of like, remember that tablecloth with the table setting experiment where you could just pull the tablecloth and everything will stay on the table. This is a similar thing. If you remove this card very quickly, okay, then the coin will fall down to the bottom of the cup. Same thing with this experiment here with the mass. Okay, if you pull on this thread very quickly, then part A or part B may break. Okay, now generally it's going to be a certain one of those, and it's actually going to be B because this mass here is going to resist the change of motion, so A will feel a smaller force than B. The example here is Voyager 1. Okay, so this is a satellite launched. Can't remember what the date is off the top of my head, but a long time ago. And at the moment, it's just kept on going and going. It's one of the first big satellites built to do exploration of space. And it went around, it took a whole lot of images of various planets in our solar system, and then they just sort of directed it off into space and let it go. There's no power, there's no engine making the thing go fast, okay? There's no rockets on it or anything like that. It essentially is just drifting in space at a constant velocity, and it's not changing because there's no resultant force on it, okay? There's no air resistance or anything like that to slow it down. So it just keeps on going. This thing here is the sort of a tablet. It's got some music on it, if you like a record player, and it's got some designs. That's for the aliens when it reaches them. So what we've got here is a block on a surface. Okay, what we have to look at here is Newton's first law. Let's look at the fact that if this thing was going at, let's say, a constant velocity, so let's say it's going down this way at 2 meters per second, okay, constant velocity, then I want to know is what is the size of the friction. So let's call it A. Now this thing has a mass, okay, let's say we give it 20 kgs. Hope you don't mind, it's going to do lots of writing in red. I might change colour soon. So 20 kgs. Now which direction does, if this thing is in a gravitational field, okay, actually we better give this thing an angle too. Let's say that looks to be about 25 degrees. Let's change colour. Oh, let's deselect something. Yeah. What should we do now? Blue. Sounds good. Okay, so this object, oh, it didn't work. This object here has a weight, okay, due to its position in a gravitational field. How do we find that weight? Well, we do mass times gravity. Okay, so that would be equal to, so it's going to be equal to 20 times, this is for argument's sake, because I'm doing it on the board, I'm just going to do 10, okay? Don't you do that. Don't be lazy, do 9.81. I'm being lazy because I'm trying to save time. So, weight equals mass times gravity, 20 times 10 equals 200 newtons. Now, what's the actual force providing the acceleration? It's the force going down the slope, okay? Providing the resistance to the friction. Because which way does friction go? Friction goes up the slope. So that is the frictional force going up that way, and so that means to keep this thing going at a constant velocity, there must be a force going down the slope of equal value. Okay, where's this force here come from? It comes from a component of the weight. So let's say I draw a triangle here. I'm going to draw it like this. And there's 90 degrees there. So this vector here, okay, that vector there is the one that's going down the slope, that is opposing the friction, and it's of equal size to the friction. So if I can work out what component this is of the weight, then I can work out the size of the friction. So how do I find that? Well, this is a 90-degree triangle. Because you've got to remember here too, is that the weight is the hypotenuse. So the only way to draw this triangle having the weight as the hypotenuse is like this. So how do I find the size of it? Well, I've got an angle there, and if you think about it, it's actually going to be 25 degrees. Okay, you guys can work that out, check it. Okay, but that'll be 25 degrees. So we've got We know the hypotenuse, and we're trying to find the opposite angle. Okay, sorry about that. Just had to find a calculator. So, working out the force. Okay, you got opposite hypotenuse. You chuck it all in, you get about 85 newtons. Okay, so that is the force going down the slope in this case. Got to move on. Describe the motion. Okay, let's say positive forces here. The buoyant force, 20 newtons. The downward force, 20 newtons. This force here, 60 newtons, and this one here, 60 newtons. Hopefully, looking at this, you'll realize that there is no resultant force, so this thing could be going, it could either be stopped or it could be going at a constant velocity. Okay, if I change one of these forces, let's say I make that one 70, then it must be accelerating forwards because there's a resultant force. Newton's second law. Okay, I need to write this one correctly. Okay, essentially force is proportional to the rate of change of momentum. Okay, so that's essentially what the Newton's second law is about. Now, if you write it in a formula, you get that. Okay, change of momentum divided by time is how fast you're changing it. Okay, your rate of change, and that's proportional to force. If we carry on from there, though, okay, we just replace the change of momentum with an equation using mv and mu. So mv minus mu is equal to change of momentum. V is final velocity, u is initial velocity. So that means we're doing final velocity times mass minus initial velocity times mass. So that's final momentum minus initial momentum. And we're going to replace time in that equation with t. So you end up with this. You end up essentially with mv minus mu over t, and that's proportional to force. What we've done here is we've taken mass out, okay, and you've got v minus u over t. Now, I hope you remember, what does v minus u divided by t look like? Okay, v minus u divided by t is equal to acceleration. So this formula here now becomes ma as proportional to force. Now, if someone actually graphed it and they found that they had 1, 2, 3 newtons up there, then the actual other values going along here would actually be corresponding. So if the mass was 1 and you had a force of 1, the acceleration will be 1. Okay? So because of that, the gradient of this line is equal to 1. So when we make an equal sign, y equals mx, so m and x, okay, the k equals 1, so we're just left with f equals ma. Okay, you can't just replace a proportional sign with an equal sign. Okay, it doesn't work. You need to put in a constant, and when you put in a constant, it can change the size of it. But in this case, the constant is 1, so we ignore it. So the formula defines Newton's second law, F equals ma. And note that the acceleration is always in the same direction as the resultant force. Okay, so if you had, let's say you had a car here, okay, and you push this way with a force, then the acceleration is also that way. However, if you push like this with a force, and it might be originally heading this way, the acceleration is that way. So what will this thing do? It's going to start changing direction around that way. You can see that later. Okay, so let's quickly do this example. The constant acceleration needed to reach the takeoff speed in 1200 meters. So what do we know here? We've got a mass, we've got some sort of displacement. Obviously, a plane usually starts from 0, and the takeoff landing speed is 60, so usually that will be your final speed. So the constant acceleration needs to reach the takeoff speed in 1200 meters. So we're trying to find acceleration in this case. Do I have room in the next page? No. So, acceleration, well, how do I find that? We've got A, S, U, and V. Okay, so V squared equals U squared plus 2AS. Okay, and we're trying to find A. So v squared minus u squared, so we're just subtracting the u squared from each side. We're going to then make that equal to 2as. We want a by itself. We're going to divide each side by then 2ns, and we're left with a. Put the values in and see what you get. What's the resultant force acting on the plane to produce this acceleration? Okay, well this is just going to be F equals ma. The F is always the resultant force. Okay, so we're going to use our value of acceleration we calculated there and put in the value of mass that we know. Okay, and should be able to get the resultant force. The thrust provided by the engines if the drag due to the ground and the wind resistance is taken to have a constant value of 10,000 newtons. Okay, now I might just need to calculate some values here, so I'll just do that quickly. I might pause it while I do that. Okay, so I'll calculate some values here. Acceleration is 1.5 meters per second. Force is 45,000 newtons. So if we look at this plane, the forward force, okay, so we've got a plane in here with a forward force of a certain amount. We've got a backwards force of a certain amount, which is 10,000. That's your air resistance. And what we calculated here was the resultant force of 45,000 newtons. So that's the difference between the forward force and the backwards force. So that means the thrust must be equal to 55,000 newtons. What we're going to do here is an experiment that we're going to do in class. If you have an object here with a mass, this thing also has a mass. This one here has a force going downwards, which is called its weight. Okay, and because of that and the tension that runs along this string, okay, tension is a force that gets transferred through a string, tension there, that's going to make this mass up there accelerate as well. So all this is based around F equals ma. The important thing with this mass is that it's the total mass. Okay, it's both of them. The force comes from the weight, and then you can find some sort of acceleration. So that's the end of part 1.